All right, we're going to take a look at this next definition of local extrema, and we're going to investigate this definition by looking at a particular graph. So, reading the definition, we'll just talk about local minimums first. If f is a function that has a domain D sub f, then for any c within this domain, we'll say that the value of f of c is a local minimum if f of c is the minimum value of f on some open interval contained within D that contains C. So that's a lot of information to parse here. But let's go ahead and look at this graph, and I'm going to go ahead and label the local one of the local minimums, and that is right here. Think of a local minimum. You should think of it as a valley or a bowl. There has to be a wiggle room. That's sort of what an open interval means. It means there's space to move around in your mathematical space. So if our mathematical space here is this number line, that's our input, then at this x equals c, we can surround it with an open interval. That means there's a little bit of wiggle room to the left and to the right. So notice here that if we take this up, our value, let's say this is x equals c for the moment, if we think about surrounding this, enclosing it in some small open interval. Now this open interval can be as small as we like, as small as it needs to be. So then if we think about lifting up these endpoints, that's going to sort of section off this portion of the curve. And you'll notice here that if you compare the y value corresponding to that point to any of these y values in this little open neighborhood around the point, in this little neighborhood, this y value is less than or equal to all of these y values. So we say in this local area, so in this immediate area, this is the minimum. That's what it means to be a local minimum. It's not saying that the function is never any smaller elsewhere. It just means in the immediate vicinity, in the immediate area, that is the smallest. Because true, over here, the y value is less than this y value. But there's a critical thing that happens, and that is this function has to turn around or something, or have a discontinuity. It somehow has to transition downward. So the idea of a local minimum or local maximum is just that in your immediate area, you can surround a location, you can swell it with a little open interval, and then anything in that interval, the value of it has to be greater than or equal to your minimum. So in fact, we actually have two minimums here. So let's go ahead and just kind of disregard some of this. We've got a local min here. We've got another local minimum. Local maximum works the same way, but we're just going to think about it's the tallest thing in the immediate area. It's not necessarily the tallest value or largest value. It's just the largest value in the immediate area. So here we've got a local max, local max. Now this value up here, at the top here, this is just a maximum. So sometimes we call this a global to distinguish it from local maximum, a global maximum. So this is not a local maximum in this case. So I'm going to go ahead and say, in this case, it's not also a local max. Because in order for an extrema, minimum or maximum, to be a local extrema, that means you have to be able to swell that point. So find a little container, an open interval, a neighborhood, an open set that contains that point. Well, if we think about dropping this point down here, then an open neighborhood containing it would be something like this, so a small little range of x values. But the thing is, while you can swell it to the right to include all these values here, they're all part of the function. the domain of the function. But if we swell it to the left, none of these x values here are part of the domain of the function. The function ceases to exist for x values less than whatever this x value is. So it's not possible to compare values of this function at this location to the left and to the right. It's not possible to do both. So this cannot be a local maximum. You have to have room on either side. And if you just terminate, it can't be a local. Now, for a second here, let's just pretend that this graph here does something else. Let's say it does this. And it continues forever. In which case, this over here would no longer be the global maximum, because this graph continues upward forever, so there's definitely larger values than this value. These all still maintain their standing as a local min or max. But what happens here, because I changed the curvature of this graph, we now get an additional local minimum. But it just so happens that not only is this the smallest value in the immediate vicinity, this is the smallest value in the immediate vicinity, it's also the smallest value everywhere. So while this is a local min, it also is a global, sometimes called absolute minimum.